Alice, Bob, and Eve explain Simon's algorithm.
Laundry day again! I've been trying to match these socks, but it's so time-consuming. I have to check each one against others until I find its pair.
Your sock matching problem reminds me of Simon's algorithm in quantum computing.
Simon's algorithm is such an elegant demonstration of quantum advantage. It finds hidden patterns exponentially faster than any classical approach.
How do my sock matching troubles relate to quantum computing?
Imagine your socks represent inputs and outputs of a special function. In Simon's problem, we're looking for a hidden pattern where specific different inputs always produce the same output.
It's like having socks that look the same, but are actually different pairs. Simon's algorithm helps us discover the pattern that tells us which socks will match.
So classically, I'd have to keep comparing socks one by one?
Exactly. Classically, you might need to check about 2 to the power of n1 socks to find the pattern with high probability. If you had 20 different socks, you might need to examine 10 of them to figure out the matching rule.
And as the number of socks increases, the problem gets exponentially harder for classical approaches.
That's precisely my frustration. So how does Simon's algorithm help?
Simon's quantum algorithm can solve this with only about n queries, logarithmically fewer. With 20 different sock types, you'd need roughly 5 quantum operations instead of 10 classical checks.
The algorithm uses quantum superposition to check all possible sock combinations simultaneously, then extracts just the information about the pattern.
How does it actually work?
First, it puts qubits in superposition, representing all possible inputs. Then it applies the function, creating entanglement between input and output qubits.
When we measure the output qubits, the input qubits collapse into a superposition of values that give that specific output, like finding all socks that could potentially match.
But we still don't know the pattern yet?
That's where quantum interference comes in. The algorithm applies Hadamard transforms, creating interference patterns that, when measured, give us information about the hidden pattern.
By running this process about n times, we gather enough information to determine the entire matching pattern with high probability.
Is this useful beyond theoretical sock matching?
While the specific problem Simon's algorithm solves isn't common in everyday applications, it was groundbreaking because it proved quantum computers could solve certain problems exponentially faster than classical computers.
It directly inspired Shor's factoring algorithm, which has serious implications for cryptography and security.
So instead of comparing my socks one by one, a quantum approach would somehow examine all possible matches simultaneously and extract just the pattern of which ones go together.
Precisely. And that's why Simon's algorithm was such an important milestone. It showed the potential for quantum computers to provide exponential speedups for certain structured problems.